Imagine drifting through a region of space where the stars have begun to bend. Ahead of you is not an object in the ordinary sense. It has no solid surface, no landscape, and no light of its own. Instead, it is a boundary in space and time. Cross it, and every possible path leads deeper inward. This is a black hole. Now, imagine the same geometry played backward. Nothing can enter. Matter and light can only emerge. A fountain with no visible source. A doorway that opens in only one direction. Physicists call this hypothetical object a white hole. Black holes are real enough to photograph by their shadows, hear through gravitational waves, and weigh by watching stars orbit them. White holes remain unobserved. Yet both appear in the mathematics of Einstein's gravity, like opposite verses hidden inside the same equation. Tonight, we will move slowly through that strange symmetry. We will visit the edge of a black hole, turn the direction of time around, and ask whether the universe could transform one cosmic abyss into another kind of beginning. First, it helps to let go of a familiar picture. A black hole is not a tunnel punched through space, and it is not a cosmic vacuum cleaner. Far away, its gravity is no different from the gravity of any other object with the same mass. If our sun were replaced by a black hole of equal mass, the planets would continue along almost the same orbits. The solar system would become dark and cold, but it would not be swallowed. The strangeness begins only when a great amount of mass is compressed into a very small region. Around it forms the event horizon, the point beyond which escape is no longer one of the futures available to you. The horizon is not a wall. An astronaut crossing the horizon of a sufficiently large black hole might notice nothing dramatic at that precise moment. Locally, space can seem calm, but globally, the route home has disappeared. To a distant observer, the story looks different. Light from the falling astronaut becomes redder, dimmer, and slower. The astronaut appears to hover near the horizon, fading into darkness. Their own clock, however, continues normally. Two descriptions, both allowed by relativity, separated by the way gravity reshapes time. The black hole itself is dark, but its surroundings may be among the brightest places in the universe. Gas spiraling inward forms an accretion disk. Friction, magnetic fields, and collisions heat that gas until it shines in visible light, ultraviolet, and X-rays. Close to the horizon, gravity bends light from the far side of the disk, wrapping it into arcs above and below the shadow. Some photons circle the black hole one or more times before escaping. Their paths build thin, nested rings at the edge of the darkness. The side of the disk moving toward us looks brighter, boosted by relativity. The far side looks dimmer. A realistic black hole is therefore not a flat dark circle. It is a lens made from curved space-time, painting multiple distorted images of the universe around it. We know black holes exist because they leave fingerprints everywhere. Stars whip around an invisible mass at the center of the Milky Way. Hot gas flashes in X-rays as it falls toward compact objects. The Event Horizon Telescope has resolved glowing rings around the supermassive black holes in M87 and our own galaxy. And when black holes collide, they shake space-time itself. Detectors on Earth record the passing ripples as a brief, descending whisper from an event that happened billions of years ago. But beyond the horizon, direct observation ends. Classical general relativity predicts continued collapse toward a singularity, a place where density and curvature become infinite in the equations. Most physicists do not treat that infinity as a completed physical explanation. It is more like a warning light. General relativity, magnificent at describing gravity, has reached a realm where quantum physics can no longer be ignored. And here, at the limit of knowledge, the white hole enters. Einstein's equations are almost indifferent to the direction of time. If a movie of planets orbiting the sun were played backward, the reverse motion could still obey the same gravitational laws. Apply that idea to the idealized geometry of an eternal black hole, and another region appears in the fully extended solution, a white hole. A black hole may be entered, but not left. A white hole may be left, but not entered. In the black hole region, Future-directed paths lean inward. In the white hole region, past-directed paths trace back toward an unreachable boundary. Matter does not climb out against gravity in the ordinary sense. Rather, the entire structure of space-time is arranged so that emergence is the only permitted direction. That does not mean astronomers expect to find a bright white sphere labeled white hole. The name describes causal structure, not color. A white hole might look like an explosive release of matter and radiation. But many ordinary events also explode. Supernovas, neutron star mergers, magnetar flares, and gamma-ray bursts. Without a unique signature, brightness alone would prove nothing. There is a deeper problem. The simple white hole seems extremely unstable. Space is never perfectly empty. A stray photon, a grain of dust, or a ripple of radiation approaching the horizon could be blue-shifted to enormous energy. In several analyses, even a small disturbance is enough to destroy the white hole configuration or convert it into a black hole. The mathematics allows the object, but nature may refuse to prepare the exquisitely ordered conditions it needs. This connects to the arrow of time. We often say the laws of physics work backward, but the universe around us has a strong direction. Eggs break and do not spontaneously reassemble. Heat flows from warm places to cooler ones. Smoke spreads through a room and does not gather itself back into a candle. Entropy, a measure related to the number of possible microscopic arrangements, tends to increase. A black hole forms naturally from collapse. Many possible arrangements of matter can end in a compact, hidden state. A classical white hole would require the reverse. Matter would emerge in a remarkably coordinated way from a boundary in the past. It resembles a shattered glass leaping from the floor and rebuilding itself in your hand. Not forbidden by every microscopic equation, perhaps, but fantastically unlike the history our universe usually writes. White holes are often confused with wormholes. The ideas are related in certain mathematical diagrams, but they are not interchangeable. In a maximally extended, eternal Schwarzschild solution, a black hole region, a white hole region, and two exterior regions can be drawn together. The exteriors are connected by what is called an Einstein-Rosen bridge. At one instant, that bridge resembles a throat between distant regions of space-time, but it closes too quickly for a traveler or even a beam of light to cross from one side to the other. It is not the stable portal of science fiction. Traversable wormholes require additional ingredients, often forms of negative energy or exotic stress that have never been shown to create a macroscopic passage in nature. Even so, the diagram poses an irresistible question. Could matter falling into a black hole emerge through a white hole somewhere else, or someone else? Classical relativity does not provide a usable escape route through a realistic black hole formed by a collapsing star. The central singularity blocks the continuation. To go further, a theory must somehow replace that singularity. Quantum gravity is the unfinished attempt to do exactly that. Describe a world where space-time itself has quantum behavior. We do not yet have one experimentally confirmed theory, but several approaches suggest that infinite collapse might be avoided. In some loop quantum gravity models, space comes in discrete quantum units. As matter is compressed toward an extreme density, quantum geometry may produce an effective resistance. Collapse could reach a minimum size and bounce. From the inside, the transition might be rapid. From far away, because gravity stretches time so severely, the same process could appear to take an immense span. In this family of ideas, a black hole may eventually tunnel into a white hole-like phase. What fell inward would not vanish at an infinite singularity. It could re-emerge, perhaps after the black hole has lost most of its mass. Researchers have built mathematical spacetimes that model such a transition, and they study whether small white hole remnants might survive for very long periods. These are serious theoretical proposals, but they are not established facts. Their details depend on assumptions about quantum geometry that experiments have not yet confirmed. Different models predict different lifetimes, signals, and interiors. The honest phrase is not, black holes become white holes. It is some candidate theories of quantum gravity allow that possibility. Another clue comes from Hawking radiation. Quantum field theory predicts that black holes are not completely black. They should emit an extremely faint thermal glow and gradually lose mass. For stellar and supermassive black holes, the process is absurdly slow, far longer than the current age of the universe. Yet it creates a profound puzzle. If the black hole evaporates away, what happens to the detailed quantum information carried by everything that entered? Quantum mechanics normally preserves information. A purely thermal cloud seems unable to remember the books, stars, and particles that formed the whole. This is the black hole information paradox. Perhaps information is subtly encoded in Hawking radiation. Perhaps the horizon is replaced by a more complex quantum structure. Perhaps space-time connects regions in a way our classical picture misses. And perhaps, in some models, a final white hole phase releases what remained trapped. None of these possibilities has won a decisive experimental verdict. The paradox remains one of the deepest meeting points between gravity, quantum theory, and thermodynamics. There is also a bolder speculation. Could the Big Bang have been a white hole? The resemblance is poetic and, at first glance, mathematical. Our observable universe expands from a hot, dense early state. A white hole sends matter and light outward from a past boundary. Some cosmological models explore whether a black hole in a parent universe could give rise to an expanding region on the other side, or whether our cosmic beginning can be described with white hole-like geometry. But the standard Big Bang model is not an explosion from one location into empty space. Space itself expanded everywhere. Every sufficiently distant galaxy sees other galaxies receding. A white hole, by contrast, is normally described as a localized region embedded within a larger space-time. Equating the two is therefore not part of established cosmology. It is an invitation to investigate, not a conclusion. Could we ever recognize a real white hole? Scientists have considered fast bursts of radiation, unusual high-energy transients, and signatures from hypothetical primordial objects. A convincing detection would need more than an unexplained flash. It would require a pattern that ordinary astrophysical engines cannot reproduce, and a theory precise enough to predict that pattern before it is found. So far, no astronomical object has been convincingly identified as a white hole. That absence matters. Black holes move from equations to evidence. Stellar orbits, X-ray binaries, gravitational waves, and horizon-scale images all converged on the same picture. White holes have not made that journey. Still, their value is not measured only by whether one appears in a telescope tomorrow. A white hole is a thought experiment built into the geometry of time. It asks why the universe chooses some mathematically allowed histories and not others. It exposes the tension between reversible laws and irreversible experience. And it gives quantum gravity theories a demanding arena in which to explain what replaces a singularity. Return now to our imagined voyage. Behind us, the stars curve around a black horizon. Ahead, in a speculative future, the darkness changes. The collapse does not end at infinity. Space becomes granular, the inward fall slows, and the geometry turns through a region no classical map can describe. Then, perhaps, the direction opens outward. Not an explosion into ordinary space, and not a magical escape hatch, but a new chapter of space-time. Ancient light, held beyond a horizon, finds a future again. Matter that seemed lost becomes part of the visible universe. The black hole and white hole are no longer separate monsters, but two phases of a single quantum story. Or perhaps nature never permits this transition. Perhaps white holes remain elegant ghosts in Einstein's equations, useful precisely because they show us the distance between mathematical possibility and physical reality. Either answer would teach us something extraordinary. Black holes tell us that space and time can close around a region so completely that the universe loses access to what lies within. White holes ask whether that closure can ever be reversed. Between them sits a question still unanswered. When gravity reaches its deepest point, does the story end, or does space-time find another way to begin?